Okay, here we are. Happy Friday. This is lecture 34. We're discussing section 5.3 of the book. The first part of the meeting, I want to have an introduction to the new thing. So I want to start by recalling what's happened this week. On Monday, we defined signed area to be the limit of sums, or our quest was we want to be able to find the signed area of curvy regions. And so we started by thinking about approximating the areas of the regions. We don't know what the area means even, but we used rectangles. And so this capital R subscript n means the right sum with n rectangles. And then we imagined what happens when n gets bigger and bigger and bigger. We realized, oh, the values get closer and closer to some number. And the idea is, well, we're going to define that number to be the signed area. So signed area is defined to be the value of this limit. So that tells us what it means, and it also tells us how to compute it. You just do this. And then on Wednesday, we defined this symbol, and the term, the definite integral of f from a to b, to mean that signed area, that limit of sums, which is just, fancy window dressing for this concept that we already had on Wednesday. One of the reasons for introducing this symbol, as I pointed out on Wednesday, is the particular details of how these limits look can vary. You can set them up in different ways so they can look different. But this symbol stands for all the different ways that those limits of these sums can look when you set them up. Now, the cliffhanger was, by the end of Wednesday, I pointed out that, computing these limits is really hard. It's kind of above the level of what we're going to do in this course. It's possible, it's in our book, and it's one of the hardest things in our book, but even that is kind of a baby version of the topic. So the question at the end of the hour was, is there an easier way to compute the exact value of the definite integral? So the answer is yes. I'm sure you're all glad you came back today. It's the evaluation theorem. Which is abbreviated ET. So the evaluation theorem says this. That's the definite integral of f of x from x equals a to x equals b. And so what the evaluation theorem says is this is equal to capital F of b minus capital F of a, where capital F is any particular antiderivative of little f. So there we go. So let me do as a first example. Find this integral. So the integral from 1 to 7 of 1 over x. Remember, you don't speak the dx. You don't say it's the integral of 1 over x dx. You just say it's the integral of 1 over x. Well, by the evaluation theorem, we have to do capital F of 7 minus capital F of 1. Okay, so our integrand, we could call that little f. That's the function 1 over x. So an antiderivative, we're going to denote by capital F. So raise your hand if you remember what's an antiderivative of 1 over x? Declare it, don't ask me. Yeah, so it's very close to ln. What's the thing we've got to add to it?
It's the natural log of the absolute value.
Yeah, so it's ln of absolute value of x. Remember that absolute value is a confusing thing. I never got it when I was an undergrad. Okay, so we're going to use this. So we have to do ln of absolute value of 7 minus ln of absolute value of 1. Now, who can simplify that? Cooper, tell me one thing I can simplify here.
Remove the absolute values.
Great, so what's that going to be?
ln of 7 minus ln.
Great, so a lot of you are fuzzy on properties of ln, that's fine, but you should all know that ln of absolute value of 7 is just 7. So this is ln of 7 minus ln of 1. Now here's the scary thing, the ln of 1 thing always freaks people out. So who can simplify this? Yeah. Natural log of 1 is 0, because e to the 0 is 1, so natural log of 1 is 0. Another way you could do it from here is, this is the same as the natural log of 7 over 1. Remember the logarithm of b minus, or logarithm of p minus the logarithm of q is the same as logarithm of p over q. But anyway, this you should know by now, or should be feeling guilty that you don't know. This is the number 0, so I get the number 7, ln of 7. That's the value. We're done. Anybody curious about that? How big a number is that? Or, let's make a picture of ln of 7. How would we illustrate this result? Well, this would be the signed area under the graph of 1 over x, from x equals 1 to x equals 7. So a picture of this number is this. So this number is the value of that area. Does that ring a bell? On Monday, when we were developing the whole theory of area, we did a worksheet. The first part of the worksheet was this thing where we had a given graph and you had to park rectangles under it to get approximations. And then the second part of the worksheet in the back was this thing. So we want to get an approximation for the area under the graph of 1 over x from 1 to 7. We did 3 rectangles. You found L3 was about, well, it wasn't about, the value of L3 was 3.07, which is too big, because you see all those green rectangles are too tall. The value of R3 was 1.35, which is too small, because you can see all those red rectangles are too short. I mean, there's all this leftover space. So that means the true value of that area is somewhere between 1.35 and 3.07. So this number, ln of 7, should be somewhere between here and here. Oh, but what else happened on Monday? I fired up the computer, and we did 10 rectangles, and 100 rectangles, and 1,000 rectangles. And what do we notice? We notice that the numbers seem to be getting closer and closer to something, and that's what led us to the idea that we define, so that, in other words, you think about the limit as the number of rectangles gets bigger and bigger and bigger, that seems to be a number. And that's how we arrived at that formula. The signed area is going to be defined as the limit of those areas. Anybody remember what that number was? Cooper?
1.95.
1.95. If you go on the computer and you type in ln of 7, you get this. 1.95, roughly. That's really cool. Now, 1.95 is just an approximation. But this is an approximation as well. I mean, look at that. That's like 50 decimal places, and it's still an approximation. The only way to write this number exactly is this. This is the exact value. So this is roughly 1.95. I love that example. All right, let me do another example. Having trouble with object permanence. Where's my eraser? There. Let's do the indefinite integral, or the definite integral from x equals 2 to x equals 8 of 1/2 x minus 2. So that's going to be capital F of 8 minus capital F of 2. So let's see, our integrand, the thing we call the integrand, is the thing inside. And we could think of that as our little f. F of x is 1/2 x minus 2. Now we need an antiderivative of that. I can use the power rule. This is x to the 1, so an antiderivative is x squared over 2. So a capital F would be 1/4 x squared minus 2x. So this is an antiderivative. I'm going very fast, sorry. But I think you can see that if you take the derivative of this, you get this. So an antiderivative of that is this. So I'm going to use this expression up there. So that thing, 1/4 of 8 squared minus 2 times 8 minus the quantity 1/4 of 2 squared minus 2 times 2. Now, I have the memory of a goldfish, so I'm going to have to just do this. I don't remember what the answer is. So this is 64 over 4, that's 16. Minus 16, oh good, that's going to turn out to be 0. And then over here I've got 4 over 4, that's the number 1. And here I've got minus 4. So this is minus a minus 3, so it's the number 3. What would be a picture of that? Well, we'd have to graph y equals 1/2 x minus 2, which is, it's going to be a line with slope m equals 1/2. And we'd have to find we'd draw the area under between that, we'd draw the region between that graph and the x-axis like this. So this signed area is going to be the number 3. Does that ring a bell? Well, if you think about what happened on Wednesday, I introduced the definition of the definite integral, with the wacky definite integral symbol, and we did this worksheet where we computed definite integrals for graphs made up of basic geometric shapes. We did a bunch of examples, and after the ones where the graph was given, we did this example where the graph was not given. We had a function, and we had to find the definite integral. So we started by just making the graph and then using geometry, and we got, what did I do here? 4, 16, 16. Huh. What? 1/2 x minus 2. 2. Because this is a mistake. None of you gets any points for this mistake because I caught it. This is the point 8, 2. So this rectangle has height 2. And so this rectangle area is 1/2 of 4 times 2. So this is 4. So this area is the number 3. So on Wednesday, using geometry, we got the number 3. Today, using calculus, we got the number 3. All right, now I want to talk about meeting part 2 is what's called the net change theorem. So in this formulation, the thing inside, we're thinking of that as the function. And the thing on the outside, we're thinking about as an antiderivative. But remember, if capital F is an antiderivative of little f, what does that actually mean? Then capital F prime is little f. That's all it means. Well, let's go back to this evaluation theorem. We can swap out that symbol, little f, and put in its place capital F prime. So we're going to replace little f of x with capital F prime in the evaluation theorem. Now when I do that, I'm going to put that over here, right? I don't want to erase that. So when I take that whole thing and I replace it, I get x equals a, x equals b, and inside I have capital F prime, and on the outside I have capital F of b minus capital F of a. So and this is called the net change theorem. It's just the evaluation theorem dressed up a different way. So again, in the evaluation theorem, we're thinking about a function on the inside and its antiderivative on the outside. In this formulation, we're thinking about the thing on the outside as being a function and the thing on the inside as being its derivative. Now, why is this called the net change theorem? Well, when you compute capital F of b minus capital F of a, you're computing a change. You could denote this as delta capital F. Change in F. So you compute the change in capital F by integrating its derivative. So compute the change in the value of a function by integrating its derivative. So the evaluation theorem over there on the right You think about what I was interested in was this thing, which is assigned area, and I can get it by doing this. In this case, you think about what I'm interested in is this thing, where I'm interested in the change in value of something, and I'm going to get it by integrating the derivative. So for example, an object has velocity v of t equals t squared minus 2t minus 8 meters per second. Compute its displacement, which means change in position. So displacement means the change of position from t equals 3 to t equals 6. All right, so we're interested in a change in position. So displacement is delta S. And so that's going to be S of 6 minus S of 1. And by the net change theorem, what I should do is I should integrate S prime. Yeah?
Is it S of 1 or S of 3?
S of 3. 3. Thank you. So what I need to do is integrate from t equals 3 to t equals 6 S prime of t. But remember that S prime is just the velocity. So I'm just going to rewrite that symbol. I'm going to integrate from t equals 3 to t equals 6, the velocity. Now I'm going to put in that formula, t squared minus 2t minus 8. So t squared minus 2t minus 8. And I'm going to integrate that from t equals 3 to t equals 6. Okay, so the integrand is my velocity, which is also my S prime, and that's t squared minus 2t minus 8. So what I need to do is I need to find an antiderivative Well, I'm going to call the antiderivative S. If the integrand is S prime, then its antiderivative I could call S. Now this is just going to be a particular antiderivative. There are lots of different antiderivatives of this. So one particular one is this one, t cubed over 3 minus t squared minus 8t. Now I'm trying to get through the lesson so you have plenty of time for your quiz. So I'm not going to go through this in detail, but you can see here I use the power rule with n equals 2. So I get t cubed over 3. Here I use the power rule with n equals 1. So that's how I got my t squared over 2, and then the 2's canceled, so I ended up with just t squared. Here I use the power rule with n equals 0. And you can also just sort of think backwards. I'm trying to sell you this thing as an antiderivative of this. That should mean if I take the derivative of this, I should get that. And it does work out that way. So what I'm supposed to do with this is by the net by the evaluation theorem, I'm going to do 6 cubed over 3 minus 6 squared minus 8 times 6. That's this thing with a 6 inside. Oh, actually, I guess what I should do, sorry, I should tell you, I should abbreviate this. This is s of 6 minus s of 3, but now we actually have a formula for it. This looks like we haven't gotten anywhere, but now we actually know what formula to use. We're going to do 6 cubed over 3 minus 6 squared minus 8 times 6. And then we're going to subtract that whole thing with 3's inside. 3 cubed over 3 minus 3 squared minus 8 times 3. And if you do all this work and you don't mess up, which if I did all the work right now, I'm not at all confident that I wouldn't mess up, you get the number 12. Arithmetic. So that, if you do all that arithmetic, you get the number 12, which means 12 meters. So the object is 12 meters away from where it started at the end of this. So that's the meeting part 2, the net change theorem. Meeting part 3 is indefinite integrals. So I want to start by just defining what an indefinite integral is. So first of all, the words. The indefinite integral of f of x. So what does that mean? It just means the general antiderivative of f of x. So something we already have a name for. And here's the symbol, which should kind of piss you off, because it's going to seem like a really weird symbol. It's that. Which should make you mad, because this doesn't seem to have anything to do with signed area. I mean, you know, the definite integral, when we developed this, yeah, Cooper? Don't steal my thunder. Oh man, I've got this all planned. But I think you have a hunch. When we get there, Cooper gets the credit for this one, I think. Give me a little symbol. What were you going to say? Yeah, okay, exactly. All right, so, you know, this symbol is about antiderivatives. This symbol is about signed areas. Why on earth couldn't we have thought of a better symbol for some, you know, why do we have to keep using that? So, for example, I just erased the net change theorem. The definite integral of 1 over x is ln of absolute value of x plus c. Remember, ln of absolute value of x was a particular antiderivative, but the general antiderivative is plus c. How about this one? Anybody remember what this is? What's an antiderivative of 1 over 1 plus x squared? Annika? Yes, yes. Tan inverse of x. And then plus c. And this is because the derivative of tan inverse of x is 1 over 1 plus x squared. That was that wacky thing. Oh, I erased the evaluation theorem. Remember that, we have y equals tan inverse of x looks like this, and y equals 1 over 1 plus x squared looks like this. So if you take the derivative, you get that. If we have a mascot for this course, it's this example, because it keeps coming up. All right, I want to introduce some more notation. Yeah, we're doing fine. More notation. Evaluation notation. Anybody know what this symbol means? You could be in France right now going, yeah.
Is that just a rectangle?
No, it's not. This means F parentheses A. So for example, and this is spoken F evaluated at A. So example, tan inverse of x evaluated at 1 means tan inverse of 1, which is pi over 4. That's because tangent of pi over 4 is 1. So that's called evaluation notation. Now there's one more bit of notation that I want to introduce. So here's the definition. You put f of x, vertical bar, x equals a, x equals b. What it means is f of b minus f of a. That's why it's called change notation. It's the change in the value of f. So for example, let's do our friend tan inverse of x. And let's put vertical bar, x equals minus square root of 3, x equals 1. Well, what does that mean? That means we're going to do tan inverse of 1 minus tan inverse of minus square root of 3. Now we already discussed that tan inverse of 1 is pi over 4, because tangent of pi over 4 is 1. Tangent of negative square root of 3 is, well, that's actually negative pi over 3, because tangent of pi over 3 is radical 3, and tangent of negative pi over 3 is negative radical 3. So the tan inverse of negative radical 3 is this. So this is pi over 4 minus a minus pi over 3. This is actually 7 pi over 12. Right, I'm like 1 minute away from finishing. Okay, so we now have the definition of antiderivative, or the indefinite integral, and we have this evaluation notation. We're going to use our notation to rewrite the evaluation theorem. So the evaluation theorem, remember, says that the definite integral from x equals a to x equals b of little f of x is this thing, capital F of B minus capital F of A. That's what the evaluation theorem says. That's a capital F of B. But now with that notation over there, we can see that another way of writing this is capital F of X evaluated from x equals A to x equals B. But remember, capital F is any antiderivative. And a symbol that we can use for antiderivative is this thing. So the evaluation theorem actually is a theorem that is a relationship between this symbol, which is definite integrals, which is about area, and this symbol, which is a calculation involving indefinite integrals or antiderivatives. It expresses the relationship between definite integrals and indefinite integrals. And the reason this weird notation, I said, why on earth do we use this symbol for antiderivatives or for indefinite integrals? You could think of it as take this symbol and just move the x equals A and x equals B over to the right and put them over here, and you've got this very different meaning thing. So that's why I think that symbol is cool. We have, in the last 30 seconds, I'm going to do this example. Let's do the definite integral from x equals minus square root of 3 to x equals 1 of 1 over 1 plus x squared. Okay, well, by the evaluation theorem, I have to find an antiderivative of 1 over 1 plus x squared. And then I have to evaluate it from x equals minus square root of 3 to x equals 1. Oh, but a while ago, we found that an antiderivative of 1 over 1 plus x squared is tan inverse. So what we're going to be doing is taking the function tan inverse of x and evaluating it, finding the change in this from x equals minus square root of 3 to x equals 1. We did that. We got 7 pi over 12. So what this is telling us is that if you take, what we started with was this symbol, which is this assigned area under the graph of 1 over 1 plus x squared. And we are taking the signed area from negative square root of 3 to 1. So this is shaded area. The value of this shaded area is the number 7 pi over 12. That's a lot to pack into an hour. The quiz is not so bad, so let's do the quiz. Thank you all. Thank you, Gabriel, for recording.